so we're talking about linear regression models, and we're going to do this example. Okay, so suppose the y variable is the annual income, and then you have these three different predictor variables. X1 is educational level, etc., okay? Number of years and gender. Okay, so yeah, notice that x3 is, we call it a dummy variable because it only has 0 or 1. It should be called Bernoulli variable, but people call it dummy variables in regression. Okay. Okay, and this is the model we are estimating. Okay, so it's a principal component main effect model, like that. Okay. Now, in a minute we're going to see how to estimate these parameters, but let's say that these are the results of our estimation using a software, right? So everything with a hat, remember, is estimate. So these are all estimators of the true values. And also we have the estimator of sigma squared, okay? Sigma hat equals 9. Okay, so given those type of models, we can answer these type of questions. For example, what is the probability that a female with 16 years of experience and 28.4 years of work, 16 years of education, 24 years of experience, will earn more than 40,000 a year? Okay, so that's our model. So y is normally distributed with the mean given by the line and sigma square, right? So when we're doing estimations, we should put hats everywhere because everything is going to be an estimator now, like that. Okay, so we compute first the mean, so evaluate the line at all these values. So female means x3 is 1, right? This is x1 and that's x2, or vice versa. But yeah, these are the values that we use. All right? So we plug in the values of the x's and multiply them by the betas, like that. Okay? So computing the probability, as we know how to do it now, we get this very little, only 5% probability. Okay? So that's how we're going to apply these models. Now, the thing is how to estimate these beta hats. And that's with the method of least squares, or ordinary least squares. Okay, so what we're going to minimize here is going to be the sum of squared errors, or SSE. Okay, so remember the square errors, so you had the line and you had the data, and then the errors are the discrepancies, right? So we're going to minimize those. Or we're going to find the betas such that that sum is minimized. Okay? So, yeah, that's the sum of these errors squared. Now, we square them because if you don't, positive errors like this one might cancel out with negative errors, like that one. Right? So, square is a good way of avoiding that. Alright, so in vector notation is E transpose E, and then so the error is the line y, the value of y minus the line x times x beta squared. Okay, so we want to minimize this function, right? So what we do is take derivatives and make it equal to 0. So the derivative of this is this, right? And it makes a lot of sense because this term in scalar form would be like 1 minus x beta squared, x times beta squared. And if you take derivatives, you're going to get this, right? With respect to beta, that is. So 2 times the parentheses times x, right? Now this is in vector form. Okay, and from here we obtain that, and then we multiply by the inverse of these matrices like this, and we obtain finally the OLS estimators. Okay, so really nice and easy. We use the concept that we always use to find the minimum or maximum of function, right? Derivative instead of equal to 0. And in matrix form, it's easy like that. It's just, okay. Now, let's, for convenience, let's define this matrix, X transpose X inverse. We're going to call it A. Right? This is going to be a shorthand notation. So that's your betas. Now, you don't need to worry too much about formulas in general in this section, because all these things are done in the computer. So don't worry if you don't remember how to invert a matrix by hand, because we're going to do all of this using calculators or computers. Okay, so the properties of these estimators are as follows. First, all the beta hats are unbiased, okay? Which is something you want from an estimator. Then beta, as you see here, is a linear transformation of the y, right? It's just a matrix times y. So it's a linear transformation. And that means that since y is normal, then beta also will be normally distributed. Well, they have the multivariate normal distribution. Okay, so that means that the beta hats are normally distributed with mean beta without the hat and with covariance matrix C of beta. Okay, and this covariance matrix, you can show that it's simply a constant, that which is sigma squared times the matrix A, that which is defined. So this is a big deal, because this is why we've been talking so much about linear combinations and normality and central limit theorem. It's because the beta hats are normally distributed, just because they're a linear combination of the y variables, which are normally distributed. Awesome. So for each individual beta, you can say that they're like the marginal distribution, right, of each beta. It's normal, and this should be an A. AIJ, I'm going to correct that. But this is right. So AIJ is going to be the IJ element of the matrix A. Let me just define it. Okay, so these are the marginal distributions of each beta I, normal, again, right? Because we know that when things are multivariate normal, the marginals are normal. Okay, and so we know the distribution of all the beta, all these betas, and again, this should be an A right here. AII and AIJ. So we know the variance and covariance, and we know everything about these betas. Okay, the same thing could be said for sigma squared. So it turns out that sigma squared hat, so the best estimator of sigma squared, is the sum of squared errors, so the objective function we try to minimize, divided by the degrees of freedom. So the sample size minus the number of parameters minus 1. And it's going to be unbiased. Okay? And furthermore, we can call it C squared as before. Right? Remember, C squared was n minus 1 times S squared divided by sigma squared. So that's kind of the analogous. So this C squared is chi-square distributed with the degrees of freedom. Okay? And similarly, as the sample mean is independent of the sample variance, here all the betas are independent of this sigma hat. Okay? All right. standard errors, remember it's just a standard deviation of the estimators in this case, of all the betas. Okay, so the first thing you want to do to test a model, to test if a variable is a good variable to include in the model, is to do the significance test. Okay, and this is going to be the hypothesis test that beta I equals 0 or not. Okay, now we're going to proceed in the same way we did the hypothesis testing for the mean. Okay, now you think of as a beta hat, you think it as the x bar, and the beta without the hat, you think of it as the mu that we had in chapter 5 or 6. Okay, so you notice it's the same logic. We have this guy that's normally distributed, then we standardize it, and we also know that c squared is chi-squared is distributed, so we're going to have all the same theory actually, right? And the t-statistic now has this form, okay, but and it's going to be t-distributed. All right, so we can go ahead and apply the same hypothesis test we did before. Now, the null hypothesis is this one always, because you want to see if the slope, right? Remember the beta is this marginal effect, or the slope of the line, right? So if the slope is 0, it means that the corresponding variable xi does not have an influence on the model. So if it's 0, you should eliminate that variable. Okay, and then the alternative is going to be different than 0, or not equal to 0. You don't care if it's positive or negative, all you care that it's significant. Okay, and significant variable means that you should include it in the model because the t-statistic is greater than the critical value. Now this guy is always around 2, so we can just use rule of thumb here. If the t-statistic of a random variable in absolute value is greater than 2, then we're going to reject the hypothesis. Okay? So you want these t-statistics for the betas, this guy's, okay? So the beta hat divided by the standard error. You want that to be greater than 2 in absolute value. That means that that variable has an explanatory power in the model. All right? Also, you can do it with a p-value as we saw before. But really, this is the main test that you do to check if that variable should be included in the model or not. The second thing you want to do is check the R-square value. Okay? It's the goodness of fit test, so how well the model fits the data. Okay. So to define it, let's look at these two figures. So on the left figure, we have the y variable and the y-axis. Actually, in both we have the y variable and y-axis. Okay? And in the x-axis, you guessed it, we have the x variable. Okay? Alright, so in the left one, you see that the line is flat, right? So that corresponds to a situation without the model, so without considering the variable x. Okay, so your predicted line, which is flat, right, slope of 0, let's say that's your model. Actually, that's the model of previous chapters, right? The way we would try to explain the variance of y was just by looking at the values of y. So you see here, these are the errors with respect to the y bar value. Okay, so that line is the average of the values of y. Okay, and the errors that you see here, so these lines, is going to be like an error term, like the EIs. And we're going to call it SSTs, total sum of squares. Okay, and it's from the data point to the line y equals y bar. Okay, and again, it represents a situation without a model. So that's your estimation of the variance of y, right? The sum of these squares is the variance of y, right? Deviations from the mean squared. And then we're going to compare that variance with the variance that you'd obtain for this right figure here. Okay, so now you see that the lines, the error bars are with respect to the line. So in the right figure, we are using the model, our linear regression model, right? And we're computing the new variance, let's say, with respect to that line. So in this case, the sum of the squares is SSC, so the original, right? The error sum of squares. Okay, so again, in the left, there's no model. So that's your estimation of the variance is the SST. But with model, and when I say model, it's obviously the regression model. Okay, with the model, then the new variance, if you will, SSC is hopefully should be a lot smaller. And that's R square, is the ratio between the two. Right, so it's 1 minus the ratio, which you could write it as SST minus SSE divided by SST, right? So that means that the R squared measures the percentage of decrease in the variance thanks to incorporating the variable x to the model. Okay? So that's the interpretation of R squared. So obviously you would like it to be as close as 1 as possible. That means you reduced all the variance. Right? That means that all the points are aligned in the regression line. And actually R without the squared is called the sample correlation coefficient. Okay? So it's kind of your rho as n tends to infinity. So it also measures, so without the square, it would be a measure of the linearity, the strength of the linear relationship. Okay, so you want it to be as close as 1 as possible. Typically, greater than 0.5 is okay. It's considered. I mean, you can, that's my rule of thumb, by the way, but, all right, anything less would be problematic. So when it's problematic, you have to revise your assumptions. Maybe it's not linear model, you need a square term, you need to add other variables, etc. Okay, so there's a problem with the R square is that when you incorporate many factors, many x variables, it tends to artificially increase. So to remedy that, we're going to divide by the degrees of freedom of each of the components, SSC and SST, remember? And those are the degrees of freedom. Okay, so by dividing by these, we correct for that error of overestimating, let's say, the correlation, because you're adding more parameters. Okay, so when we have a single x variable, then either will give you the same result, but when you have several x variables, then you want to use the adjusted R square. And the interpretation would be very similar. It's the same interpretation. Now, it turns out that you can express it also as 1 minus your estimated variance divided by the sample variance of y. Okay, remember the S square on chapter 5-ish, 6-ish? So it's the same but for y here. Okay? Yeah, the form is 1 over n minus 1, and then the sum of the squares of the y's. Minus y bar squared. Okay. So So again, right, this is the variance of y, so with respect to the y bar, which is the flat line, and this is the variance of the linear model, right, which is the bars with respect to the regression line. Very good. Now this is going to go really quick because I don't find it very useful myself, but you have to know at least the wording. Okay, so this is ANOVA. ANOVA means analysis of variance, and it's an output that you will see in every software package doing these type of analyses. Okay, so what it does at the end is test this hypothesis right here, which is rather, I've never found it useful, because you're testing that all parameters are 0, right? Which is, it's not very useful because you want to test each parameter separately. All right, so okay, let me just say that. All right, so it starts with this identity that we're not going to prove here. All right, so we already talked about the total sum of squares and the error sum of squares. Now we'll introduce a new one, is the regression sum of squares, which are the differences between the predicted value y hat, right here. It's just a regression line evaluated at the estimated betas, minus the mean of y squared. Okay, so it turns out that's an identity. It's not immediate, but it's true. Okay, and then we come up with this statistic called the F statistic, right? Very similar to the adjusted R-square formula. And it turns out that this guy has the F distribution. Now we haven't talked about F, but because I don't use it very much. But you see here is the ratio of two chi-square distributions. Okay, all these things with sum of squares, they're all chi-square in statistics, right? Because remember what the chi-square was. It's the sum of, it's not a normal squares. All right, so the ratio of two chi-squares divided by their degrees of freedom turns out to be an F distribution. And then there's probability tables and what to reject or accept H based on that. Okay, that's all I want to say about ANOVA. Okay, assessing the model. So here we're going to check the assumptions of the model. Okay, so we estimated everything, we have our output. Now we need to see if it's a good model or not. Alright, so we already went through, let's assume that they have a good t statistic, right? All greater than 2 in absolute value. That the R square is good, okay? More than 0.5 hopefully. And remember also the sign of the betas have to make sense. Okay, and at the end we're going to do the model assessment. So making sure that the assumptions of the models are met, which are these three that we've talked about before. And hopefully that will be the case. Okay, so the main tool would be the residual plots. And remember, the residuals are just the error terms once they are realized. Right? So the error terms are normally distributed, that's the assumption. Then you estimate the model, and then you're able to see what the actual error is, right? Which was right here. The actual error is this one, right? The sum of squares error is the actual value of y minus the predicted value of y, given by the regression formula. Oh yeah, I need a little I there. Yeah. Okay. And then the residual plot is just, so plotting those guys against, typically against one of the x variables or just versus I. It doesn't really matter what. But the thing you're looking for is that there's no patterns in the residual plot. So these are examples of good residual plot. So in the top row you see the regression line and the data. Okay, the dots are the data, the line is the regression line. The shaded areas, don't worry too much about them. they're just confidence intervals, well, confidence bands. Anyway, so top row is the model, bottom row is the residual plot. Okay, so these are, in the y-axis you have the residuals, and here it's against the x variable. Right, we're doing a weight versus height regression. All right, but again, you can plot it against weight also, and plots are very similar. But yeah, the typical is to plot against one of the x's. When you have more x's, typically you plot it against the fitted values, okay, or the observed x's. Anyway, so what you want to see here, the dots are the residuals, right? So you want to see no pattern. Now this figure, the line, these wiggly lines represent the mean, like a moving average mean of the errors, of the residuals. So you want it to be flat, right? Like, so the first one is perfect, you don't see any pattern, and the mean seems to be 0, okay? So you're looking for something like this one, no pattern. Okay, the middle one is bad because you see a parabola arising like that. So up and down, that means non-linearity for the most part, right? And if you look at the data, yeah, maybe a better fit would be obtained by this type of non-linear curve. So when you see a pattern like that, and there is typically non-linearity. Now, in the third one here, the problem is that the variance is not constant, right? Because at the beginning, all points are kind of cramped up, very close together, but at the end, they're a lot scattered. There's a lot of scatter, okay? And so the variance, which is the deviation from the mean, which should be 0, here you see that it grows a lot. All right, so this one's good, and these ones are not. Okay. The second tool would be the QQ plots. All right, QQ stands for quantile, also known as normal probability plot. All right, and is this type of plot right here, where you're gonna have typically in the x-axis, you're gonna have the theoretical quantiles. So remember the quantiles like the percentile function, right? Right, theoretical quantiles or percentiles versus the observed. So from your model quantiles, right? And the theoretical come from the normal distribution, right? Because you want to think, this is the plot we use to check normality. Okay, and we're going to use this method because it's faster, I guess. It's more an art than a science, right? Because it's just using your eyes. And what we're looking for here is a straight line. So the first column is great, the second column is not so good, right? So you're looking for a straight line because it's a quantile versus quantile plot. So the theoretical and the x-axis and the observed. So if there's a perfect match, you should see a perfect line. Okay? Now, these type of deviations at the tails are very typical, and you shouldn't worry about it too much if they look like this. Now, this one's perfect. There's a little bit here, but so that's very useful, common, that you have discrepancies at the tails. Now, yeah, the second column are examples of bad QQ plots. And basically that's going to be our model assumption verification process, just looking at those two type of plots. Right, so again, in the residuals, you look for no pattern, and then in the QQ plot, you're looking for a line, straight line. All right, now let's do an example trying to put everything together. This is our data. So the y variable is 8 cases in the US over time, and these are quarterly periods, so just time. Okay, so you see the relationship is increasing like that, but kind of parabolic. So we're going to fit a model that is a parabola, right? Beta naught plus beta x plus beta 2x squared. So that's going to be your parabola term. Okay? All right. So we put the data in the software package, and this is a typical output. Okay, so you have the variable, the coefficients, right? So these are the betas, beta hats, actually, right? I should put a hat everywhere. You have the standard error of the coefficient, so the square root of the variance of the betas. Then you have the t value, okay, which we call t naught in the lectures, right? And that's the value, the testing of the hypothesis, right? That beta equals 0. So here you're looking for values that are greater than 2 in absolute value. So these are all a check, right? They're all significant variables that you should incorporate. And here's the famous p-value that we also talked about. So you can either look at the t or the p-value that give you the same information, right? And we said that a low p-value or a p-value less than your alpha is better, right? Because then you're rejecting h naught, which is that beta equals 0. All right, so you see that they're tiny p-values, meaning that they're very significant. The betas are very significant. Now, significant means that they are not equal to 0. Okay. Next thing we look is the R square, 0.99. That's awesome, right? That's a perfect fit, almost. All right, that's your estimation of the variance. That's sigma hat right there. And that's your objective function that we try to minimize, right? So yeah, that's another way of saying the same thing. So here's a good model, okay? In terms of the t-values and the sign, well, the signs of the time, yeah, are hard to interpret, so we're not going to look at that now. But the t-values are awesome. The R-square is awesome. Now let's look at the residual plot. Do you see a pattern? I mean, you can always see patterns, right? But in this case, it's not so evident. Right, so the spread here is comparable to the spread over here, so the variance is kind of constant. It's true that you see this pattern, but it's alright. I mean, I would be able to sleep at night with this type of residual plots. Normal plot, it's pretty close to a straight line except for here, but yeah, it looks okay. There's nothing too bad, you know, to say that's a bad model. Okay, so that's an example of a good type of models. All right, so the next topic is how to select the right model. So in the 8th case, we were lucky. The first model we tried, I guess, was a good one. But in general, you have so many choices of factors, right, x variables, that is kind of overwhelming to choose a model sometimes. Okay, so here we're going to give you a few pointers, and the best one is Occam's razor, which in a word is simplicity. You're always looking for simplicity in your models. The simpler the models, the better they are. They're more robust for predictions, they're easy to explain, easier to maintain, to update, etc. Alright, but so the key of Occam's razors, or the law of parsimony, is that so you have different models that have a similar explanatory power, and then you choose the simplest one, which would be the one with the least number of factors. That's a measure of simplicity, is the number of x variables you have in the model. The other is the nonlinear terms. So if you have a square term and a linear term for the same variable, So a square term is more, let's say, not as simple as a linear term, etc. But in general, the main variable or the main strategy, I guess, it's given the same amount of explanatory power, right? Given similar r squares, right? You would choose the model with the least number of parameters, least number of betas, right? Okay. So these is like my checklist. So the first thing you would try to do is if it's a main effect model, right, you check the signs of the beta, because then recall that in that case you can interpret the betas. Okay, so if the signs are correct to intuition, that's good. Next step is you want a good adjusted R square. All right, the closer to 1 the better. Then you want good t-stats for all your betas, and you want to make sure that all your assumptions are met in the model. Okay, so that's our checklist that we should check for every model, and then choose the best one. Okay, so let's do an example of this type of problems. Now, today we have software packages that are able to estimate all possible combinations of all the possible variables, x variables you can imagine. So at the end, what we have to do is analyze the output of this software, okay? And so that's kind of the focus here. We know how to compute these models, but we're going to let computers do it for us. We're going to use our knowledge to choose the best model, which is where computers struggle. All right, so let's look at this data set, which is about housing values in Boston, okay? And these are all your x variable. Your y variable is going to be the price of the house, okay? Yeah, you might want to pause the video and read what all these variables look like, right? And then we let the computer estimate this type of model, right? Multiple regression model with, up to p variables. You can include them all, you can include a subset, etc. Okay? And then these are typical questions and that's your y variable, right? It says the medium house price. Okay, and these are the type of outputs that you'll be presented with. So you have each row is the model, right? Model 1 through 6 in the screen. We have the adjusted R square, and then we have the parameter table. Okay, so yeah, the first row is the name of the beta, second is the value of that parameter, and third is the t-statistic, the t-naught, the t-statistic for each beta, okay? And then you have the residual plots and the QQ plots right here. So everything nicely, concisely set up here. All right, so let's analyze a few. All right, so the first model, pretty good R square. Comparable to this one, right? So 0.7, 0.72, right? So all the others, they're too low of an R square. Now these two, let's leave them for now. But yeah, the other two compared to the 0.7s, right? So first is you want explanation power, right? So at least 0.5. Okay, so now we have to choose among these. Let's take a look at a couple of beta. Right, the second thing I would do, let's look at the values of beta. The signs of beta. All right, let me do just a couple. All right, beta 13 is negative, okay? So let's make sure that makes sense, right? Because our model is a main effect model. So the betas are the marginal change in y given a unit change in the corresponding x value. So it's the derivative. So 13 was lower status of the population. Let's pick another. I don't know what that means. 11. What is 11? Pupil-teacher ratio. Okay, that's a good one, right? So, pupil-teacher ratio. So you want that number to be large, right? That means it's a good school. You have right. You have fewer students per teacher, right? So you would think that the more pupil-teacher ratio on a town, the house price would be higher because you have better schools surrounding. So it should be positive. Yet we have a negative value there, so that could be problematic. You see? Unless I interpret it wrong. But pupil to teacher, yeah, you want that. Wait. Is it teacher pupil or pupil teacher? Pupil teacher. Oh yeah, I got it wrong. Yeah. So it's good. That is negative, right? Yeah, it's pupil divided by teacher. I thought it was the opposite. Anyway, so that's good now. Because you want this number to be low. Right? So if this number is low, you want the price of houses should go up. Alright, so it's good that it's negative. Sorry about that confusion. Alright, let me just do another one. Beta 9. 9, index of accessibility to radial highways. Okay. Accessibility, so the more accessible, the better, right? You're more connected. So it should be positive. Because more accessibility should give you a higher price. Okay? But it's negative. So that's problematic. Right? Alright, so you should check all the signs like that. Make sure that they make sense. Alright, one more, beta 4. 4 is... Alright, so if you're close to a river. Okay? So people want to be close to a river, so it should be positive. And yeah, this one was positive, so that's okay. Alright. Next thing we're going to look is at the t-values. Now look, here's a small t-value, so it's less than 2 in absolute value. That means that beta 9 is not a good variable to include. Okay, now maybe that explains why we obtained a negative value for the beta, because the variable wasn't significant. Okay? So, yeah, I'm not liking this model because we have that extra variable that shouldn't be there. Alright, let's keep going. The one in the bottom, yeah, I don't like that one, right? That's a very small t-value, 0.92. All the rest are fine. Let's assume that the signs are okay. This one, you see the sign of beta 9 is positive. So I'm liking this model better. Alright? Okay, and then the residuals, so these look okay. I mean, this is weird. There's a kind of a pattern like that I don't like. Yeah, this is totally a pattern. So, no. Yeah, these were bad anyway, but yeah, too much of a pattern here, here as well. This is better, right? That's pretty good. Alright, QQ plots, they're all okay, except for this one. Maybe that's a little too much. Alright, so the winner is model 6, according to my analysis. Alright, so that's the kind of analysis we're looking for, right? Like putting everything together like that. Right, and then you have more examples. And this one's similar, but it's colored in red, means that the t-statistic is less than 2. So it's even easier to spot. All right, if you click on that, there's hundreds more examples like that, okay?